All right, folks, I make it 3 o'clock, so I'm going to start. I realize people are filtering in, but I've got housekeeping and preamble, so we'll just get through that. My name is Ian Cooper. You can find my socials there. We have Twitter. I post less there now. And we have Mastodon, for those of you that have kind of joined an exodus from Twitter to Mastodon, given the health site's become even more of a health site. This talk is really about the idea of reactive architectures and how we can use some of those ideas and what it means when we think about building our own distributed systems. Who am I? Most of this just says that I have a big grey beard and I'm quite old and I've been doing this for a fair amount. I currently work at Just Eat Takeaway. Locals can blame me for non-delivery of their food if they wish. And the point I always raise is the one at the bottom, right? I and some other folks in this room got started speaking because we started the .NET user group in about 2003 when there literally were no experts. So we had to give talks ourselves. And as a result of that, we kind of got past that initial hurdle of fear about standing up in front of other people and talking. And that went on to enable us to start speaking at conferences, et cetera, around the world. And I would encourage any of you to consider doing it. And any of you may think to yourself, I have nothing to say. That's because you think about the things that you and your peer group know. There are people who want to learn from you about the things that you know that are valuable to somebody else, perhaps at an earlier stage of their career. Right? So please do step up if you feel like it. I work on an open source project. Any .NET developers in the room? Yeah, loads of you. All right. So we are an alternative to mass transit, end-service bus. I can't remember what Jeremy Miller's now renamed his as, Wolverine or something. We are an alternative messaging and mediator-style framework. All right, what am I going to talk about today? I'm going to have a little diversion into objects. I'm sure we all know about objects, but I'll have a little diversion and talk about how objects may have colored our thinking of the world. And then I want to look at how reactive in its ideas may give us a different way of thinking about how we build distributed systems today. Reactive is mostly not based on particularly new ideas. So we'll talk about some ideas like data flow, actor, flow-based programming that all really date from about the 1970s. Like many ideas from the 1970s, we're revisiting them because they were kind of ahead of their time. They weren't really successful. But when we move into a modern context of multi-core architectures, distributed computing, it turns out some of the ways these ideas were working are incredibly valuable to us in changing our perception about how we do stuff. So we'll look at a few of those old ideas, and then we'll try and address this idea of what people mean by the idea of reactive architectures and how these old ideas play out for us in trying to build systems that have properties of being resilient, elastic, and responsive. Okay. Objects. I'm sure everyone in the room knows about objects, right? So we have a class, and the class encapsulates some data, right? Generally, well, most of our data to be in private fields. And then there is some behavior that it exposes. And normally, there's coupling between this behavior and this state. Right. The state that we need in order to exercise this behavior, or alternatively, the behaviors that are associated with knowledge of this state are kind of coupled together in a class. Right. And then we may choose to compose classes by having, the fields be a class themselves. We might, in the bad old days, have thought we'd inherit from behavior from another class. We do that less now because that turns out to be very fragile. But we've got this orientation of data and behavior living together. And generally, although we talk about this being message passing, what they really mean is I call a method, some parameters to message in, and it gives me a response as a message out. I made this idea called dynamic dispatch, right? I'm not too worried about that. Just this idea, effectively, that you might call from a base method on something you inherit from. But we all know about objects, right? Great. So when we first started to build component architectures, service-oriented architectures, there's really kind of an early name for these component architectures, but there are lots of them. Even before SOA, really we had, COM and Corba, etc. The dominant paradigm was objects. So this is basically, you look at kind of SOA through the lens of, say, WSDL. So WSDL had an idea, effectively, where I got a service, and has some operations on it. And the operations are things I can send in a message and return a message. It's like a method on a class, really, that was just the parameters we sent to the operation and return value. Right? And it had some data. We had the kind of 4 tenets of SOA, and we said, oh, yeah, well, basically what happens is the class basically hides all the data, and then you provide operations on it. And then WSDL had things like an endpoint and a binding, right, often called the ABCs, address, binding, and contract, that let us expose basically this service to other people. Classically, usually there was a URL, and we bound SOAP in order to basically reveal this thing to the outside world. But what that led us down the path of was tending to think of our systems when we broke them up in terms of, I want loads of little objects with their behavior. So typically when we thought maybe about an e-commerce application, as an example, we might think, oh, well, I have restaurants, and I can create and read and update and delete restaurants, so I need a restaurant service, and I have accounts for customers, and I create and read and I update and delete accounts, so I have an account service, and so on, and so on, and so on, and so on. That tends to be a little bit of a problem. And we get a couple of negative characteristics from that, and we also get them in OO, to be honest with you. And one of them is this idea of feature envy. If I tend to have these object-like services, where does the logic tend to go that uses these services with their operations? On the client, maybe in some kind of API gateway, right? Maybe, effectively, it drifts all the way down to one of the first services, like a shopping cart, that becomes a kind of God service that says, don't worry, when someone wants to basically make an order, I've got all the business logic. And what you tended to find in SOA was that we ended up with these services that were very much, most of these things just do CRUD, and the shopping cart has all of the domain logic for our e-commerce application. And that's kind of negative, right? Because really, we kind of know that that's going to cause problems for maintenance. Because every time somebody wants to make a change, this God component's got to change, right? So the God service has to change every single time. And that isn't really what we meant by autonomous components or independent deployability or all those things that were supposed to bring us the dream of our teams being able to work independently of each other. And this OO paradigm that we were kind of pushing forward has kind of fooled us a bit, right? And in some cases, I used to joke to people and say, well, if I've got an accounts database and I'm doing CRUD on it, and it's actually over a store like DynamoDB that has a REST interface anyway, what does my service actually do? Why not just call Dynamo? But we see a lot of these services out there that are really, when you reduce them to what they're actually doing, they're just a thin wrapper over the API of the database. The other problem is that they tend to work via RPC. Or asynchronous conversation, let's say, because quite a lot of them also work via HTTP. And the problem with that is that faults propagate. If I lose my menu service, then it turns out the cart can't get hold of the menu anymore, and it probably can't price the order that you've given me for my food, for your food takeaway. So as soon as menu stops working, everything stops working. I became vulnerable in terms of my availability to customers to the least good coder in the organization. Right? Your uptime is the worst programmer you have, because when his code fails, the whole house of cards comes down. And your team working on the restaurant service, you may have built something that, you're pretty sure it's resilient as hell, but it's useless to you if the guy who's working on menu, had a bad day and the code is pretty useless. So we get these problems, and some of them are really to do with the paradigm of, hey, it's just really a big object that we talk to basically via often, gRPC, because then it looks like a procedure call, right? And it's just an object I'm using remotely. And this kind of remote objects paradigm has kind of killed our attempt to do autonomous components a lot. So in the 1970s, reactive was really a kind of alternative to the dominant paradigm, really about von Neumann machines, but then later on, essentially against other programming paradigms. And they fought a continuous struggle against things like object orientation, and in many cases they lost, right? Although there are successful examples of these systems that emerged, they didn't become mainstream to a large extent until we got into distributed systems later. I'm going to warn you, I don't want to talk today about specific implementations. So there are lots of tools out there which would badge themselves as reactive tools, RX, reactive streams, active frameworks like Erlang, Akka.NET, or whatever, right? This talk is not about that. So that's what you want. There's still time to run away. I'm not going to get into the depths of a specific implementation. What I want to look at is the principles that reactive programming had, and how we can apply those principles to how to build distributed systems. Any one of those tools may be helpful to you, or none of those tools may be helpful to you. You don't need any of those tools to implement these ideas, right? Okay. So what is reactive? Well, reactive can be divided into a couple of things. Reactive programming, which is really what we had in the 1970s, things like data flow programming, actor models, flow-based programming, and reactive systems, which is this modern concept, which is really a whole load of, if you like, principles and patterns that you can use for implementing distributed systems. But they all have a core idea, and this quote really comes from via Paul Morrison, JPM, who basically is the man behind flow-based programming. My Greek is terrible. It's something like ta panta re kai uden mena, which it just means everything flows, panta re, and nothing stays. Uden mena. The Greeks in the audience can tell me how badly I've mangled that. I apologize to anyone who's Greek. The idea, it's a quote from Heraclitus, who was a philosopher, is that we should really be focusing on flow, right? On the passage of things, rather than on these little isolated entities. Okay. So data flow programming is one of the kind of oldest beasts in this space. And it says, what we want to do is think about our program as a graph. And in our graph, there are nodes. And at those nodes, some kind of behavior happens, right? Some kind of transformation. And between those nodes, over the vertices, flows data. And so I want to not join these two concepts together, but kind of separate them. The idea of saying, hey, data is flowing through my program, and then it reaches these particular nodes, things happen. And you can pretty much program anything using this model, right? You can program addition, right? Number hits the node, another number hits the node, I add the two nodes, add the two together, put the result out basically from the node, right? And so these things work to basically let us do complex programming problems. And generally, when you see data flow programming today, those of you who are .NET devs, there's quite a few of you, there's things like TPL data flow. Liam has got a talk probably somewhere on the internet you can find if you want excited to learn about TPL data flow. Is that the one with the kettles, Liam? I can't remember. No. Okay. So you have to have a node, and the node you can think of as a black box. a unit of computation. Right. And my node has kind of input and an output. We tend to think of them as ports. So some data comes in, the black box performs some magical transformation, and an output goes out. I push a kind of answer out onto the wire. Typically, what tends to happen is I create an instance of the node because there is some work available on the input, do the work, push the answer, close down basically that particular node, right? So I respond to there being work. Some of you may think about data flow programming in that idea of saying, hey, I've got this whole set of jobs to do. Data flow programming lets me spin up things to do those jobs. But really what we're trying to focus on data flow programming is this idea of a flow of work and transformations you are performing upon it. And the key is, the data rather can be anything pretty much. Data flow programming has no real restrictions, right? It could be simple flat data, it could be primitives, it could be compound, structured, unstructured, doesn't really matter, right? But the key is I can begin to chain these things together. So I can create little simple behaviors that are easy to understand, and I can chain them into more complex behaviors. The poster child for this is obviously the Unix command line, right? Where I got little programs that do things and I pipe the output into other things. But we can write programs like that, where we just have little simple transformations and we just basically push work through all these transformations. Okay. So we can be synchronous or asynchronous here. So in synchronous, basically what happens is the thread of execution flows down the chain, or we can be asynchronous, which tends to require buffering. And what tends to happen there is essentially each component, when it puts out its answer, puts it onto a buffer. So the next component doesn't have to be available at that point in time. It just picks up the work when it's ready from the buffer. Okay. And that allows data flow programming to work basically in parallel, right? So we can have these various steps working in parallel with each other. So it's an easy model of basically using multiple cores in an architecture, or even in the modern world of using multiple systems, because effectively the idea is that this individual item can be simple and single-threaded. The multi-threading comes from running them all in parallel, and they just simply read work off the buffer. Typically, when we can think about push or pull, sometimes hot or cold is another word for the same thing. Are we effectively observing something that is essentially spitting out data and we're just listening to it? Canonical example is usually a mouse moving around, generating in Windows, I think it's WM mouse move messages, right? Or are we effectively saying to something by a pull, hey, please start sending us information about X? We also tend, in data flow programming, to say the output buffer, because it has a fixed capacity, should not be full if I effectively want to read. In other words, if I'm going to do the work, there's got to be space for me to put the work out there. And that allows me to apply something called back pressure, right? That says, hey, if the downstream is all jammed up, the buffer's got full, it can't work as fast as we can, we should pause and wait until it's done some work, freed up some space on its buffer, on our output buffer, its input buffer, right? Freed up some space, and then let us write. And this basic idea of back pressure says we want to essentially prevent things being overwhelmed. Because if they're working in parallel, they could be working at quite different rates. And ultimately, we're all subject to the law, which I can't remember Amdahl's law, which basically says, you know, our overall throughput is limited to the throughput of the slowest component in our chain. Okay. So classic lifetime is essentially, as we said, I effectively live long enough to basically calculate the answer. And capacity is essentially that these buffers have capacity. They're not infinite. I mean, in theory, in maths, you could probably make them infinite, but in practical computing resources, that never happens. And you have back pressure by not basically taking work off an input queue until there's space on the output queue for you to write stuff. Now, a nice advantage of this model is that we tend to benefit from being loosely coupled because these individual components are only coupled by data. Okay, quick recap. Coupling, some various examples of tight versus loose coupling. Content coupling is, I know about your code, your schemas, everything else. Common coupling is, we both share some global data. That could just be a big database table. Control coupling is, I have certain flags or signals I send you to control the behavior, the way you do stuff, which so your internal behavior has a dependency on the flags that I know about, right? Stamp coupling is where essentially you only use a portion of the data that I send. There are fields that are effectively unused. And data coupling, which is kind of the weakest form of coupling, says we're both coupled by the schema of the data that's passing between us. We have to have some coupling in life. I mean, not necessarily, but it tends to be nowadays that machines running in locked basements with no connection to the internet are pretty useless for any real work. So we tend to have some form of coupling to other things, right, in order to be useful, necessary coupling. So data, if we're going to choose some coupling, is a good form. One of the other ideas that reactive programming was trying to get into is actors. What are actors about? It's one of those words, but like monoids that people get frightened by. So Edgar Dijkstra basically said, hey, sometimes we have mutable state. And sometimes we have multiple threads. And it would be really bad if the threads altered that mutable state in the wrong order. How do I stop that? Oh, I know, I'll have some means of doing synchronization, some kind of gate, tend to think about semaphores, monitors, etc., which means that we serialize access to that mutable state, right? Only one thing can affect the mutable state at a time. And that was the dominant paradigm, how we did multi-threaded code for how we protect mutable state from being basically corrupted by multiple threads running at the same time. And you have probably written or used code that essentially uses a semaphore or a monitor in order to protect basically mutable state. The actor model, it says, well, we could look at the kind of data flow programming model, and if we say that our node is single-threaded, then our node, the single thread, is the only thing that can update the mutable state. Then if effectively I think of my input buffer as a kind of inbox, then I can protect access to that mutable state because essentially there's only one thread ever altering it, and it's just stepping its way through the work requests in the inbox. So I don't need a synchronization primitive of any sort because effectively this model gives me synchronization of my mutable state. So this is basically Carl Hewitt, and he called this the actor model, but really it's just a variation of data flow programming. An actor is just a data flow node. It's just taking advantage of the fact that if I make my node single-threaded, I can sequence the changes to the mutable state that it protects. Actors have some basically rules around them. Actors can send messages to other actors. They can create new actors. They know the addresses of actors, and they can basically communicate about the addresses of actors. Don't worry too much about that. Why do you care? The main reason you care is because, obviously, if I think about the fact that I'm protecting mutable state in an actor, I might have lots of mutable state that I want to sequence access to. How do I do that? Well, generally, the idea is that I can partition all these actors that own parts of the mutable state and effectively route requests to the right actor to essentially update the relevant piece of mutable state, right? So that's really how actors scale. Obviously, if I have one thread, now one thread will get you a long way, and we underestimate how fast one thread can be, but it may be too slow, and in which case I need to partition my state and work with one thread instead. Just as an aside on this, I mean, we build systems using things like Kafka every day, right? And on a Kafka partition, you have a single thread. You're only allowed to have one thread ready from a partition at a time because you have to retain ordering. And I can't retain ordering if I have multiple threads. Because if I have multiple threads, there's no guarantee as it reads item off the queue that it won't process them out of sequence. So Kafka says, hey, a given partition on a stream, only one thread gets to read it. And what we do is we effectively take that stream and we slice it into a number of pieces. Well, a technique called consistent hashing, which basically says, given a restaurant has an ID, it always goes into this particular bucket so that I can always process updates to it in order. So I get away with having one thread. So we build production systems all the time in a single-threaded approach. And single-threaded code is simple and easy to write because I don't have to worry about multi-threading concerns in the code itself. What I do is rely on the partitioning to give me that single-threaded approach. Right? And a Kafka stream, a partition on a Kafka stream, is effectively a mailbox from which I can read to get work I update. Right? So I'm not specifically using an actor model, but the same understanding about how stuff works is useful to understand to apply. Flow-based programming. So flow-based programming is probably less well-known than the other two. Anyone heard of flow-based programming in the room before today? Okay. Poor old JPM. Flow-based programming is another form of data flow. It's got some interesting ideas, so it's worth raising it as well as data flow. So I have a node, just like in data flow. It has ports. Ports generally name data flow programming, in flow-based programming, rather. And one of the reasons ports are named is because with your code running inside the node, you just address a named port. You say basically, hey, receive from the port called in, send to the port marked out. You tend to give them more meaningful names, but in and out will do us for high level. And then what that lets us do is say, you internally don't know anything about the connector. It's external to you, the thing that connects you to other nodes. So it could be replaced by something else, right? It might be in memory in one environment, but actually in your production environment, it's a RabbitMQ message queue. Okay. So that's one idea that it brought in. So idea of named ports. And really, when we think about channels in messaging, which are really, we talk about them being a virtual pipe with a logical named address, it's really just another version of this idea from flow-based programming of a named port with an external connector beyond it. And the idea in flow-based programming is we have information packets, data, and it flows between nodes, and those nodes are black boxes that perform some kind of transformation on it. And the result of that basically is work, right? So information packets essentially are deleted from the buffer. You read them from buffer, you delete them. You process your work, and you put a new information packet out on the far side representing the transformation. In messaging, quite often we talk about queues versus streams. Streams from like Kafka. We have an index. It's effectively an append-only stream, and we just basically record how far we've read. We keep a track of how far up this stream have I read, and we tend to store that in something called an offset. In a queue, we tend to actually lock the next item on the queue. We read past if it's already locked. We delete that item off the queue. The queues are much more similar to the way that flow-based programming works, and it says delete that incoming piece of work so nobody else processes it, it's done, and move it along. Okay. So the node essentially in flow-based programming can actually suspend. So rather than the data flow programming model where effectively we spin one up, push some work through it, shut it down, and then when the next item of work, spin another one up. In flow-based programming, we're allowed to actually suspend it. We're allowed to say, there's no work, so I'll just pause, doing nothing until some more work arrives, and I can send you an explicit kill signal. I say basically, hey, there's no more work to do. You can kind of give up and shut down now. Right? And with capacity in flow-based programming, as well as the decision to say, hey, there's no capacity on the output, so effectively, I don't want to basically send you something, in other words, back pressure. I can also do load shedding. Flow-based programming says, you know what? If you receive an input and there's no room on the output, you're perfectly entitled to dump the input. And that can be useful. So think about context, for example, we have information packets all the time from riders who are out there trying to deliver your food. If I miss some of those, it doesn't really matter, because I'll get another signal a bit later telling me where it is. All you'll see is that the rider seems to jump on the map. like they're teleported. That's simply because we've just dumped some information packets because we were feeling overwhelmed, right? But it doesn't really matter to you. At some point, we'll catch up and then we'll show you where somebody is. So load shedding is a viable option at some points. There are some rules. If I'm writing to basically an output port, I only get to do that on one thread, so as to preserve ordering. But many people can write to an input thread, but obviously, effectively, that will impact the ordering of those things that I have. Okay. There's some other interesting ideas. Initial information packets. So when I start up my node, I can have basically a port where I read a single packet, and that packet tells me how to configure myself. Anyone program with MQTT and IoT devices? A few people. So MQTT has a similar notion of an initial information packet that lets you configure a consumer when it starts up to start receiving messages. Okay. And control packets, or brackets as they're sometimes called, this idea that I have a sequence of messages I want you to process where I give you basically an initial control packet, sometimes called an opening bracket, a whole set of messages that then relate to that particular piece of work, and then a closing bracket packet, which basically says that's the complete set of work that you need. But another one we'll come back to is the idea of a lookup table. So the idea that says I might need some data in order to do my work. That data could be generated by another node. And what I do is I listen to the output port of that other node, and I put basically the results of its work into a table, and then I can go and look it up. So I want to go and look up prices of food. There may well be a node A where effectively you are entering changes basically to menu item prices. It does, I don't know, some calculations on VAT or whatever effectively and gives you the final, and our service charges, it gives you the final price. And your little lookup node says, I take that and I just write it into a database. And then when B, which is doing some pricing of an order for a customer, comes along with basically a customer's order as its information packet, it can use the lookup table to figure out the price. And what that stops the need for us to do is to call A to send it a message saying, can I have the price for X? Can I have the price for Y? And keep sending it messages because we have to suspend the workflow in B for that pricing item while we wait for the request response to come through. So if we pre-build that lookup table, it makes it very easy to do that pricing. And we'll come back to that idea. Okay. A drink of water. It's not a magic trick, it's just drinking some water. So what are reactive systems and how do these 1970s ideas, how do they help us? So there's a big document, don't worry, you're not intended to be able to read that. You can go and find it on the internet. It's called the Reactive Manifesto. It was written by Jonas Bonner, I think that's probably correct pronouncing it, and a whole load of other people you have probably heard of helped. And their idea was that a whole lot of people were working on similar sorts of ideas, and they wanted to produce a manifesto that talked about what they perceived as a better way of building distributed systems. And so they defined what you can think of as an architectural style called reactive applications, and they had some rules, right? So they had the rule that they should react to events. And this event, in a sense, that is basically the definition of reactive for them. It reacts to events. Right. What that lets you do is think about basically reacting to load by being scalable, being resilient to failure, and being responsive to users. So generally, the mantra is that effectively they are responsive, resilient, elastic, and message-driven. Don't worry about the detail. You'll go through this a few times in the next few seconds. And you can find it there. So this is kind of the diagrammatic version, which is a little bit easier to read. Okay. By the means of being message-driven, we obtain the properties of being resilient and elastic, which enables us to be responsive to users. That's effectively what they're driving at. Okay. So reactive systems use message passing, and we explicitly mean by that they're going to send, have an asynchronous conversation between any two components. It may or may not be messaging middleware, right? And effectively what we're saying is, hey, I'm going to send you a message, and when you're going to do your work, and you're going to basically send a message out as a result of doing that work. It might be a reply to me, or it might simply be a signal to the next person in the chain. So effectively, there are a couple of things that may be going on. You're probably receiving a message, and it's one or two options. Look on the bottom. You're either being given a command, right? You're being told to do something, or you're being given facts, things you should know. Typically in messaging, we think about these as a command. I'm telling you to do something. Well, often my common example is make me a cup of tea. And things that basically you know. You may be given facts on Ian's tea preferences, right? Ian likes his tea white. He doesn't like any sugar. He prefers basically English breakfast. Under no circumstances give him Earl Grey. Right. Earl Grey is dirty dishwasher. This dishwater is not tea. All right. So typically, these components that receive these commands or events, when we think of them in terms of distributed systems, we tend to call them services. We should think about them doing transformations in response to these pieces of data they receive. Often, what you're looking for is something you can name as a verb-noun combination. I do this to this. Right? I place an order, I onboard a restaurant. You don't want a restaurant service, you want an onboarding restaurant service. That's what we do. We onboard restaurants onto our platform. Right? And so what you want to think about is what transformation are you performing in this process? And then like data flow programming, effectively we chain these together in a flow. So here, potentially, I have said, here is a customer purchase. I want to check out the purchase. Or probably in this case, you might want to rephrase that as I want to price and validate the purchase. Right? So I take your purchase, your basket of all the items that you've ordered. I figure out the pricing. I apply any offers. I validate that essentially maybe that stuff's in stock. And then I say, I need to take a payment for that. So I send this priced order, because now I can take a basically payment for it, onto the next component, which essentially is going to price it. Typically, what you're looking for when you're influenced by this reactive model is things that you can run in parallel. Your one service, you don't want to be doing things that could be done in parallel. Because it's much easier to split out the thing that could be done in parallel into a new node, send a message to it. Because then essentially, you could potentially think about making that component single-threaded, just getting it to run, pulling work off a queue. Right? But you can scale each one of those items quite independently of each other. So think quite often about a model of processes, tasks, and activities. You can, if you want to, use something like value stream mapping to figure out your process chain in your organization. And what you want to do is think, hey, what things actually could occur in parallel at different steps of, if you like, my production line, where I'm just passing work down to get processed. This idea of coordinating our data flow, orchestrating a continuous steady flow of information, focusing on division by behavior, not structure. Let's talk a little bit about Pat Helland. So Pat Helland basically is an architect, been at Amazon, Microsoft. You should probably go and read most of his papers if you haven't. He's exceptionally influential in terms of the world of autonomous computing. So when we think about what this process does, I find it helpful to think about Pat's model of basically what happens inside a component. And Pat basically has this idea of an activity. So at the bottom, so an activity is just basically a state machine. And it says, I've received a message, I should do something in response. Probably I may choose to update a resource. So a resource is something that belongs to the business that I manage. I don't know, restaurants, couriers, right? And I typically also have, I may have some state about an activity. If I'm my state machine, for some point I need to actually say, well, I'm going to stop the state machine there in order to wait for a response from a different node. I may have to save the state of my state machine into database. We'll come back to that in a second. You may not need to. So the activity is generally this combination of code that I run in response to an input signal and any state I need to store about my activity to allow me to resume it if I crash or I need to pause for any reason. There is an explicit boundary. In other words, the things inside my activity state, my resource state, they are not exposed to the outside world, right? That means, effectively, I know who is effectively going to be basically reading and writing to it. I could choose to be single-threaded, right, for example, because I know there's no need to worry about synchronization because, effectively, I'm the only person writing to it. I also protect these resources, their schemas, etc., such that I can change them and nobody outside cares. They only care about the thing that comes in on the input port and the thing that leaves by the output port. So you might have a model like this, right? Purchase comes in on my input port. I begin my activity. So I say, oh, I need to check out. What do? I validate the order. Is that a valid? You know, can the restaurant still cook that? Sometimes restaurants take things off menus for us because they run out of the ingredients necessary to cook it, right? Then basically we may price it. Pricing may involve offers, right? You know, currently it's a Cheeky Tuesday offer and you're going to get 15% off. Then what we want to do is request payment for this order, right? So what we do is we just basically pause our state machine, save some state, saying, hey, we reached the point of payment made, and we send a message saying, hey, let's grab the payment for that, please. That goes through our output, off into the ether, right? And then the next component does the pricing, and when it responds, comes back by a different port, right? Comes back by a port saying priced order. We can use a correlation ID typically to look up that particular piece of activity. Say, where did we get to? Oh, yeah, we basically had requested payment. Looks like the payment's been made. I can move this order on, and I can send out another signal, for example, saying new order, and that will then go to order placement. So I'm building, just like in data flow programming, a kind of black box, which I then effectively have these activities inside, and they just communicate with the outside world by messaging. I need to worry about transactional messaging because, well, actually, it should be my activity really more than my resource, but if I'm effectively saying, hey, I suspended my workflow at the point of making a requested payment, I need to send that message. Generally, one of the problems that I hit is I can't effectively usually have a transaction that spans both my messaging provider, my broker, be that basically Kafka, Rabbit, SNS, Azure Service Bus, whatever you use, and the resource, where I'm storing probably more my activity state than resource state, right? In order to make sure that those two are in sync, so that if effectively I say I have requested basically the payment, there has been a corresponding message, I want a transaction. The way I do that is I create an outbox. So generally a table in the same place effectively I'm managing my activity state. And I write the message there. And then a sweeper, usually some kind of separate thread, looks through the outbox for unsent messages and sends them for me. And it keeps doing that on a regular interval. And eventually, even if the broker is temporarily down or unavailable, it will send it. Because it ain't going to mark it sent until it's gone. So at that point, I can guarantee that I have transactional messaging. There are risks. I don't want to get into that today. Let's not talk about outbox. That effectively I can duplicate sending because I don't get to write basically back to the outbox. So we call it guaranteed at least once. We call it guaranteed at least once because you have to accept the presence of duplicates. And that means I tend to want an inbox. An inbox so I can deduplicate. Have I seen this piece of work before? If I have seen this piece of work before, I probably shouldn't process it. And what's really useful about this is essentially this component can crash. If it crashes before it's basically sent a message to onto the broker, when it comes back up, there's no dispatched entry in the outbox, so I'll keep trying to resend it. And because I can guarantee that I've got messaging and other components have inboxes, so they cope with duplicates, I'm okay with these components crashing. Interestingly enough, I may not even actually need to save activity state. If I have an inbox and an outbox, I actually have a record of the conversation that I've been engaged with about a particular activity. I know what I've received, and I know what I sent. I could recalculate what activities are currently in flight because I say, well, I received all these and I haven't sent those messages out, so they didn't reach that point. Or this one reached that point and I'm waiting for a response for it. So you can recalculate it. You don't have to necessarily do that, but in some cases you might want to see that as an optimization. Okay. So generally these things are sequenced together. So here, effectively, my price goes over to take payment. Take payment does its work. At some point, basically, it says a payment was made. That comes back on a different port. I advance the workflow in my state machine so the purchase has been made, and then I raise a new order. Even if that basically is an error, that's just another message being raised. If the customer's card was declined because effectively they'd taken the card off basically some forum in the deepest, darkest parts of the internet, then it turns out basically that's okay. It's just a payment refused message, and we effectively then would just raise a request new card message. Right? So everything is just messages flowing back and forth. Okay. Now, interestingly enough, like we said, what this protects us from is when we looked at that early idea that basically entity services faults would propagate, because we have asynchronous conversations between these components, work simply queues. So if it crashes my take payment module, I simply queue up payment requests. When it comes back online, it'll start basically honoring those payment requests for me. So we talk about this being a bulkhead to failure. Bulkhead's this idea on a ship. I have these watertight compartments. If I receive a hole in a compartment, just the compartment floods, the whole ship doesn't sink, right? The take payments is down. That's a problem for the team on call for take payments, but it doesn't necessarily mean the checkout team have to scramble. Their work's just building up. Hopefully the queue won't get too long before we basically introduce a new instance to take payment and it works. By the way, don't beat the Titanic. The Titanic basically, for its first-class passengers, didn't want to have to navigate those hatches on bulkheads. It stopped its bulkheads short of the top of the ship, so first-class passengers could allegedly stroll along the deck. Only problem with that is, when one of your bulkheads gets a hole in it, the water floods over the top to the first-class, basically, passenger compartment, and your ship sinks. So be wary of that. Probably our closest example to making holes for the first-class passengers is this idea sometimes you see people get all the way to doing that model and then they go, oh, I need a pricing model to price with. How am I going to get that? And they forget that I'm building my model in a reactive style where effectively I have data flow programming style nodes message between them. I'll just do a GET request and get the pricing model, which is, of course, a bad idea because now, effectively, I've just reintroduced a dependency basically on a synchronous component that, if it faults, brings down my checkout component, right? Now, admittedly, only checkout is probably down at this point. That may not be so bad. Everything else is queuing, but we can still work around that, right? One option might be, well, I send the model a request to the pricing component, say, can I have the pricing model for this restaurant? And it replies and gives it back to me. But in this kind of data, like pricing models for restaurants, actually I'm going to be asking for that a lot. So the other alternative is to think about that model from flow-based programming of a lookup table. And we say, well, I'll tell you what, the pricing component, whenever it basically creates a new pricing model, a new catalog or a menu, if you like, it sends out a message. I'll listen for those, and I'll store them in a database locally to me, and I can just look up the pricing. Because it's not an activity I want to parallelize, and so essentially I don't really want to put my workflow into basically, I don't want to basically shut it down and say, save the state away of my activity, wait for the pricing model to come back. That's quite inefficient. Right? I just want to price it there and then. So I can give you the data that you can then use to price it by listening to the event stream that's coming out of the pricing module that says, hey, here are some facts about prices. Remember this idea, we have two things that messages may be. An instruction for us to do something, please do this, purchase something, or things that you should know, like a pricing model. And it turns out what I do with that is I save it so I can look it up later. This general idea is called event carriage state transfer. What that means, the pricing model is down, I'm resilient to that too. Sure, the prices are a bit stale, but that's generally okay. Right? Maybe you get a cheap pizza. We live with that. There are another whole forums on the internet dedicated to how you rip Just Eat off, by the way. So sometimes we can tailor the consistency here, right? We can decide what's our ability to live with something that may be eventually consistent, that might be a little bit out of date. If that's okay, maybe we can use some technique like a lookup via ECST. Maybe we can't really live with that, and I have to send you a message and get a response. But you can tailor the consistency that you're willing to accept in an individual component. Okay. We alluded to this earlier. Let it crash, right? It comes from the actor model. This idea that we say, hey, the simplest thing for us to do is to accept that in the event of a failure, we should probably just rapidly crash our application. Recovery's hard. Writing all that code that figures out, I wonder what state we're currently in, and I wonder how I can unwind this mess, is probably fraught with error and peril, right? Because generally speaking, you don't know enough, and what happens if you crash while trying to recover from the crash, right? It's a bit of a nightmare. Generally, a huge number of crashes, it turns out, you can just get resolved by basically saying, let's just kill this system and basically reboot it. Right? Turn it on and off again works for nodes as well as anything else. But to do that, we have to make sure that startup basically is recovery. When we start up, we figure out where should we be, and shutdown is clean. When I shut down, I don't leave things in a state I can't recover to. So, some simple rules. If I'm pulling something off, basically an input buffer, don't ack it, don't say I'm done with it, until I've sent a corresponding output message, updated my activity state to the right place, marked it in my inbox. Right? Until that point, what will happen is if I crash, the work will still be on the queue, and I can simply pick up the work again and try it again. Right? So don't mark that individual piece of work done until we've done it. Okay. Deduplicate, because somebody else may be sending us duplicates, because they've been using transactional messaging to make sure that we're going to receive the messages that correspond to the state they've currently reached. And use asynchronous messaging because that allows us basically to let them crash and we just queue work for them. We're not dependent on their uptime. We haven't forced them to be available. We just want availability of their asynchronous messaging middleware. We may need to apply back pressure, just as we did with basically actor models. If we have to control the rate at which we can consume stuff, generally it means we've got a resource that basically is limited in its capacity. So maybe we're using a database with a JDBC connection coming out of a pool. We've got a limited number of connections in the pool, all right? Two ways of applying back pressure, depending whether we're push or pull to the messaging middleware. If basically it's pull, fairly straightforward, we reduce the rate of polling so that we don't effectively get too many messages. If it's push, typically middleware tends to support the idea of only X many messages in flight. So if I have a certain number of unacked messages, it won't send me more. Okay. We may also want to think about a circuit breaker. In the event that stuff that we own is struggling with the load, then just basically stop taking messages. wait until a certain amount of time has passed, try a test. If that one goes through, hey, open the floodgates and let everybody else back in. Or alternatively, load shed, right? So in the event that this resource is struggling, that's okay. I'll just discard incoming messages, and I'll wait until basically it recovers. And overall, we can also think about the idea of being single-threaded. If our components tend to basically be single-threaded and reading from the queue and writing to the output, they're very easy for us to reason about. As software engineers don't have to worry about serializing access to immutable state. We don't have to worry about context switching. The open source framework I work on, Brighter, we are single-threaded. You can have more instances of us, but we're single-threaded. And we scale far better than complicated schemes I've seen where people write them with thread pools and it's all a nightmare, right? Try to be single-threaded. If I'm single-threaded, I obviously have to think about the fact of, well, if I introduce more instances of them, am I now at risk basically of trying to update things out of order because I'm pulling work from two threads, from a stream, so I put things out of order. I said earlier about Kafka. Kafka can let you read with one thread through partitions. So if you need ordering when you choose to scale out a single-threaded item, then effectively you have to rely on partitioning of some sort. Active models do a different form, but they still do partitioning effectively when they route. Right? If you don't care about ordering, if I can process these items individually, I can just scale out without worrying about it. I can have a queue or the like. It doesn't necessarily need to support partitioning. All right? Okay. So I can scale out these components, which means if I let something crash, it's pretty easy for some kind of supervisor to just create new instances to continue to meet my workload. And that's where you get Kubernetes from, or other forms of elastic, basically, compute that will introduce new instances in order to cope with instances that have gone down. Okay. And overall, that gives us this idea of responsiveness. This idea, essentially, that's a hard diagram to read. This idea that, effectively, if we have components that essentially communicate via asynchronous messaging and therefore have bulkheads to failures of other components and can easily be scaled out such that as components begin to fail, we can just introduce new instances in order to replace them, we tend to be responsive to users because we can both scale to meet load on demand and we can remain working despite failure. Which gets us back to this diagram, which is really where reactive architectures come from, which says, if we choose to build applications that use messaging as the means to communicate between the different nodes of our application, we will gain the benefits of resilience because we have bulkheads to failure, elasticity, particularly if we have a kind of let it crash pattern, where essentially we just basically restart new components in order to cope with the failure of existing ones, or essentially to cope with increased load, or also to cope with decreased load and reduce our cost, right? And that makes us responsive to users. And all of that really comes from us reapplying some of these ideas from the 1970s that came when people were trying to think hard about how we would cope with a model that had multiple cores and not necessarily the classic von Neumann architectures that were prevalent at the time. All right, and I'm done. I don't think we have much time for questions because I think I'm bang on time. But as I'm packing up, if you've got a question, feel free to come up at the front and ask. So thanks very much.